Hi and welcome to John's Maths book. In this video we're going to be looking at complex numbers and vector subtraction on the Argand diagram. If you like the video then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go to the whiteboard. In an earlier video we explored complex numbers and their representation on the Argand diagram, noting their vector-like properties of magnitude, known as the modulus of the complex number, and direction, known as the argument of the complex number. We plotted complex numbers 2 plus 3i and 3 plus 2i and represented them as vectors OP and OQ respectively. Adding these complex numbers produce a new complex number 5 plus 5i represented by vector OR. Visually, we demonstrated vector addition OP plus OQ by placing the tail of vector OQ at the head of vector OP, resulting in vector OR. We observed that adding OQ to OP yielded the same result, and we described this process as commutative. Furthermore, we showed that this could be visualized as forming a parallelogram, with the resultant vector OR represented by the diagonal. To subtract complex numbers using vector arithmetic, we can adapt the addition process. For example, if Z1 is equal to 2 plus 3i and Z2 is equal to 3 plus 2i, then subtracting Z2 from Z1 can be expressed as 2 plus 3i plus and then minus into the bracket of 3 plus 2i, which simplifies to 2 plus 3i plus and then in the bracket minus 3 minus 2i. On the Argand diagram, minus 3 minus 2i is represented as a vector diagonally opposite to 3 plus 2i. In vector terms, subtracting the vectors is equivalent to adding the negative of vector OQ to vector OP. Visually, this involves placing the tail of the negative vector OQ at the head of the vector OP, shown here. The resulting vector OR then represents the complex number minus 1 plus I, the result of the subtraction, on the Argand diagram. Now let's explore the multiplication of a complex number by a scalar and its representation on the Argand diagram as a position vector. Consider the complex number Z1 equals 2 plus 3i, represented by the position vector OP. If we multiply Z1 by the scalar value of 2, we obtain complex number Z2, which equals 4 plus 6i. This can be represented on the Argand diagram by positional vector OR. Notice here that positional vector OR has the same direction as OP, but a magnitude twice as large, indicated by the fact that the line that connects the origin with point R is twice as long as that which connects the origin and point P.